Let's recap our lesson on the photoelectric effect, as well as go over our post-lab calculations and graphs. Around 1900, scientists were shining lights on metals. They knew electrons were inside. That was discovered by J.J. Thomson. And so they reasoned that these electrons could be ejected by light. Their understanding of physics at the time made two predictions. They thought that the intensity of light was proportional to the energy of the light. And that was reasonable because a brighter or more intense light carries more total energy. So given enough time and intensity, any light, even low-frequency red light, should eventually be able to eject electrons out of a piece of metal. Their second prediction was that the kinetic energy of the electrons would be proportional to the intensity of the light. In other words, brighter lights should eject electrons with greater kinetic energy, or higher speeds. But experiments showed that this wasn't the case. Shining even the brightest red light on a certain metal ejected no electrons, no matter how intense the light was, or how long it was shined on. But when they shined a light with a smaller wavelength, or a higher frequency, let's say green light, electrons were ejected instantly, even if that light was very dim. So that was very puzzling to them. And it seemed that the kinetic energy of the ejected electrons only depended on the frequency, or the color of the light, not the intensity. For example, shining a higher frequency light, like blue or violet, ejected electrons with even greater kinetic energy. This phenomenon is known as the photoelectric effect. And at this point in our lesson, I asked you to illustrate several relationships graphically to gauge how well you understood the concept. So why don't you try that again now, without looking at your notes. Let's start by drawing a graph of the number of electrons ejected as a function of frequency of the incoming light. So pause the video and try to draw that graph without looking at your notes. Your graph should look something like this. For this given metal, let's say the threshold frequency is here. Below this frequency, no amount of light is able to eject any electrons. However, when the frequency of the incident light is greater than the threshold frequency, then electrons are ejected. But that frequency only tells you whether electrons are able to be ejected, not how many electrons are ejected. That's dependent on the intensity of the light. Think of it as each photon or particle of light is able to eject one electron. So that incoming photon has to have enough energy to eject an electron, but it's not going to eject more electrons. Now draw a graph of the kinetic energy of the emitted electron as a function of the intensity of the incoming light. In other words, how does increasing the intensity of light, or the brightness of the light, affect the velocity or kinetic energy of the ejected electron? Here's what that graph should look like. Keep in mind the kinetic energy is proportional to the frequency of the incoming light, not how much of it you have, or the amplitude of the wavelength, or the intensity of the light. No matter how intense a light you shine on a piece of metal, if that frequency of that incoming light is below the threshold frequency, you're not getting any electrons. And if you shine a light with a frequency greater than the threshold frequency, you will get electrons ejected. But shining a brighter light won't eject those electrons any faster. You'll just get more electrons. By the way, this graph only applies to when the frequency of the light is greater than the threshold frequency. Otherwise, there are no electrons ejected, therefore no kinetic energy of ejected electrons. Now finally, let's draw a graph of the kinetic energy of emitted electrons as a function of the frequency of the incident light. Let's say this is the threshold frequency of this metal. Below that threshold frequency, again, there are no ejected electrons. However, after we reach the threshold frequency of the metal, increasing the frequency of the incoming light will increase the kinetic energy of the ejected electrons. So just think about that intuitively. If you shine a light with enough energy to eject electrons, any additional energy can go into the kinetic energy of the ejected electrons. And by the way, I've been using velocity and kinetic energy kind of interchangeable, but they're not the same thing. But I've been doing that because kinetic energy is equal to 1/2 mv squared. And since the mass of electrons are the same, the kinetic energy in this case is proportional to the velocity. Now let's take our most recent graph and plot several metals on the same graph. We use rubidium as an example. It might look something like this. Next to that, we'll plot potassium. Potassium has a higher threshold frequency than rubidium, so we'll put that somewhere to the right. And after that point, again, as the frequency of the incident light increases, the kinetic energy of the ejected electrons from that metal will also increase. And we'll do the same thing for one more, and we'll do sodium next to that. And so that might look something like this. So in 1905, Einstein looked at this photoelectric effect and solved this puzzle. When you look at this graph of multiple metals, no matter which metal you have, the slope is always the same. And Einstein predicted that slope to be Planck's constant. And he was right. So Einstein's looking at the photoelectric effect. And a few years earlier, Max Planck gets the same constant appearing when he's studying blackbody radiation. So that same number is appearing in two different phenomena. And if you think about that, that's the universe telling us something. But back to these graphs. Since these are all lines, we can describe them in slope-intercept form. Y equals mx plus b. And we can extrapolate these lines to get the y-intercepts because we have the x-intercepts. At the x-intercepts, we know that the kinetic energy of each of these is zero. So 0 is equal to Planck's constant, which is the slope, times the frequency, which represent the x values, plus b, which is the y-intercept. So solving for b, we get that the y-intercept is equal to negative Planck's constant times the threshold frequency. By the way, this is also known as a work function. Represented by the symbol phi. But you don't have to know that for our class. We'll just continue to use the concept of threshold frequency. Therefore, these lines are described by the kinetic energy is equal to Planck's constant times the frequency of the incoming light minus the work function. And Einstein was able to use this to explain the photoelectric effect, namely by proposing that light's energy is delivered in packets, these discrete packets known as photons, and each photon carrying an energy proportional to its frequency. So in other words, light has particle-like behavior. We'll get to more of that in our upcoming lessons. But now let's move on to our post-lab calculations. Here we ask to calculate the kinetic energy of the electrons that are ejected from the metals lithium and banana beryllium by UV light. So instead of just doing the problem for you, I'm going to choose another metal and work out the problem the same way. So I'll work out this problem using palladium. So here's what we're going for conceptually. Each of these metals has a threshold frequency where the incoming light has to overcome to be able to eject electrons out of these metals. And since the frequency of light is related to its energy, by Planck's constant, we can say that the energy of the incoming light has to be greater than the work function, or the energy required to remove this electron. And then any additional energy that that light has will go toward the maximum kinetic energy that these ejected electrons can have. So let's start by turning this frequency into a quantity of energy. We can use the equation energy is equal to Planck's constant times frequency. We're given the frequency of palladium, so we're going to multiply that by Planck's constant. And there's the energy required to eject electrons out of this metal, palladium. This is also known as a work function. Now let's see how much energy is in ultraviolet light. We were given the wavelength of ultraviolet light to be 370 nanometers. So let's convert that to frequency, and then we can turn that into energy. Let's turn wavelength into frequency using this equation. We're going to isolate frequency, plug in the values for the speed of light and the wavelength of ultraviolet light. Now we can turn nanometers into meters by slapping on 10 to the negative 9, because 1 nanometer is 10 to the negative 9 meters. Now that we have the same units, top and bottom, we can cancel out meters and punch these in a calculator. And we have our frequency of UV light. Now let's plug this into E equals h nu to get the energy of this light. So there's the energy of the ultraviolet light that we used. Now notice the energy of the light is greater than the work function, the energy required to eject electrons from palladium. That threshold energy is going to eat up this amount of the incoming energy from the light, and any remaining energy is going to be the kinetic energy of the electron. So all we need to do is take the energy of the light, which is greater than the threshold energy of the metal, and the difference is going to be the kinetic energy of the electron. So when we shine UV light on the palladium metal, we get electrons ejected with a maximum kinetic energy of 4 times 10 to the negative 20 joules. Finally, let's move on to the graphing section. You were asked to draw a graph of the kinetic energy of the emitted electrons as a function of frequency. So we just did this a few times. We're told to add the graphs for the two metals that you just calculated, lithium and banana beryllium. I'm going to go and add the graphs of all of them because we're given the threshold frequencies for all 5 metals. Banana beryllium has the lowest threshold frequency. So I'll plot that first. Calcium has the next lowest threshold frequency. So I'll plot that somewhere to the right. And a little bit more than that is lithium, followed by palladium, and followed by gallium. We know that once the frequency of the incoming light is greater than any of these threshold frequencies, we're going to get electrons ejected. And with increasing frequency, we're going to get faster ejected electrons. And we know this slope is going to be Planck's constant because that's what Einstein predicted. And turns out that he's right. So that's how you would graph all of these metals on a graph of kinetic energy versus frequency. Now we're asked to label the 4 lights that we use in our lab on the x-axis. Let's start with the red light. Where would the red light go on the x-axis? Now we're given the wavelengths of light, but we don't need to do any calculations because experimentally we know that the red light was only able to eject electrons from what is this thing called? Banana beryllium. So we know that the frequency of the red light must have been greater than the threshold frequency for banana beryllium. But it wasn't able to eject electrons from any other metal. So we know it was less than the threshold frequency of all the other metals. So we can say the frequency of the red light falls somewhere between banana beryllium's threshold frequency and calicium's threshold frequency. Now the green light was able to eject electrons from both banana beryllium and calicium, but not any of the other metals. So we can say the frequency of the green light must have been greater than the threshold frequency for calicium, but less than those for lithium, palladium, and gallium. And the blue light was able to eject electrons from banana beryllium, calicium, and lithium. So we know the frequency of blue light must have been greater than the threshold frequency of lithium. And then finally, the frequency of the UV light, which we just calculated. So you can just use that number and plop it right there, right between the threshold frequency of palladium and gallium. And finally, to label the equations for each of these, you're asked to do lithium and banana beryllium. So I'll plot the equation for what did I do earlier? I'll do it for palladium, and so you can figure it out for lithium and banana beryllium. So the equation for the line for the graph of palladium using the slope-intercept form, y equals mx plus b. Right. So the kinetic energy is on the y-axis. The slope is Planck's constant. X is frequency. And the y-intercept is the work function, which is Planck's constant times the frequency of the metal, the threshold frequency. And there is our y-intercept for palladium. And there is our slope-intercept form for palladium, or at least all values of x, or frequency, that is greater than or equal to the threshold frequency of palladium.